Hey everyone, in this section we're going to be talking about sum and difference identities. To start off, go ahead and let alpha and beta be some angles. Then we're going to get the following identities for sine, cosine, and tangent. The first sine identity goes as follows. The sine of the sum alpha plus beta can be represented as sine alpha cosine beta plus cosine alpha sine times beta. And we also get a very similar identity for the sine of the difference between the angles alpha and beta. The only difference between this formula is a plus changes to a minus. We then get the following identities for the cosine of the sum and the difference of alpha and beta. Again, each expression looks pretty similar with the change of sign in the middle. And then we have the following identities for the tangent of the sum and the difference of alpha and beta. Now, even though these formulas look like a lot, you'll notice that each sign difference counterpart virtually looks the same, where I'm just changing from some pluses to some minuses and vice versa. Now, instead of just proving trig identities like we did in the last section, we're actually going to use these identities and identities that we'll see in the next section to solve equations and to help us with computations. So to get started, we're going to use these new identities to find the value of sine of 75 degrees. And the only reason that we couldn't do this before is because 75 degrees is not one of the special angles on the unit circle. So the trick is going to be the following. We're going to see if we can express 75 degrees as a sum or a difference of special angles. Notice that 75 degrees is the same thing as 30 degrees plus 45 degrees. So I can represent 75 degrees by two special angles of the unit circle, which I can put through the sine and cosine functions and get known values for. So to put this into action, express the sine of 75 degrees as the sine of 30 degrees plus 45 degrees. Then we're going to use our sum identity to express this as sine of 30 degrees times cosine of 45 degrees plus the cosine of 30 degrees times the sine of 45 degrees. And even though I do have a lot more terms here, I can actually use the unit circle to compute each one of these values, when I couldn't do that before. We'll get that this is equal to 1 over root 2 times root 3 over 2 plus 1 over root 2 times 1/2, which when we simplify, comes down to the square root of 3 plus 1 divided by 2 times the square root of 2. So this is what we would call the exact value of the sine of 75 degrees. In a similar spirit, let's look at the tangent of pi over 12. Obviously, pi over 12 is not a special angle, and the difference here is that it's a little bit harder to represent a fraction as a sum or difference of other fractions because those have a few more moving parts to them. So the trick here will be to take pi over 12 and convert it to degrees, and we'll find that pi over 12 is equal to 15 degrees. If we're trying to realize 15 degrees as a sum or difference of special angles, and we think about it long enough, we might find that 60 degrees minus 45 degrees is the same thing as 50 degrees. And 60 and 45 can be reconverted back into radians, which will be pi over 3 and pi over 4 respectively. It's okay to convert an angle to degrees just to help us see certain things a little bit more clearly, but since the original problem was stated in terms of radians, we do need to convert back. So we're going to go ahead and rewrite the tangent of pi over 12 as the tangent of pi over 3 minus the tangent of pi over 4. And then we're going to put in our corresponding trigonometric value for this difference. This will give us tan of pi over 3 minus tan of pi over 4 divided by 1 plus tan of pi over 3 times tan of pi over 4. Of course, pi over 3 and pi over 4 are special angles, so we can start plugging in the corresponding trigonometric coordinates, and this is going to give us the square root of 3 minus 1 divided by 1 plus the square root of 3 times 1. And this is simply going to simplify as the square root of 3 minus 1 divided by the square root of 3 plus 1, and this is going to be the exact value of the tangent of pi over 12. For our next problem, we're going to find the exact value of the cosine of the cotangent inverse of 3 over 7 minus the sine inverse of 2 divided by 3. We've seen problem types that resemble this in section 7.6 when we were talking about inverse trig functions, and one of the best tools that we could use in this setting was to draw a right triangle. Since I have two inverse trig functions at play here, I need to draw two right triangles. First thing I'll do is I'll take the first expression, cotangent of 3 over 7, and set it equal to the angle alpha. And then I'll take the sine inverse of 3 over 2 and set it equal to the angle beta. Now alpha and beta are just variable names I'm picking for the angle outputs that I would get from these trigonometric values. But now I'm going to flip this around and establish that the cotangent of alpha is equal to 3 over 7 and the sine of beta is equal to 2 over 3. So the cotangent, recall, is adjacent over opposite, and sine is opposite over hypotenuse. So I'm going to draw a triangle for each one of these angles, and I'm going to label the sides accordingly. The first triangle for the angle alpha will have an adjacent side of 3 and an opposite side of 7, and the second triangle, the one for beta, will have an opposite side of 2 and a hypotenuse of 3. Using the Pythagorean theorem on both triangles, we can solve for the missing sides. The alpha triangle will have a hypotenuse length of the square root of 58, and the beta triangle will have a horizontal length of the square root of 5. Now that I have all these sides figured out, I can complete the rest of the problem in the following way. Let me take the original problem statement and replace cotangent inverse and sine inverse with alpha and beta respectively. This is now reducing our problem to the cosine of alpha minus beta, which I can replace with the cosine of alpha times the cosine of beta, plus the sine of alpha times the sine of beta, using our new sum identity. Now, I'm not using the unit circle for this problem anymore. I have two right triangles with expressions like cosines and sines of alphas and betas. I simply am just computing the cosine and sine of these alphas and betas using our regular trig ratios. So this means that the cosine of alpha is going to be 3 over the square root of 58, and the cosine of beta is going to be the square root of 5 over 3. Likewise, the sine of alpha is 7 over the square root of 58, and the sine of beta is 2 over 3. So even though this problem might look just a little bit daunting, it all comes down to drawing triangles and filling in all remaining sides. And then it just comes down again to using our regular trig ratios to solve and complete the problem. After some number crunching and simplification, we'll end up with the expression of 3 times the square root of 5 plus 14 divided by 3 times the square root of 58, and we're done. This is going to be the exact value of the cosine of cotangent inverse of 3 over 7 minus sine inverse of 2 over 3. Our next problem is going to be virtually identical, but instead of using numbers like I did before, we're going to use the variable x so that we end up with a purely algebraic expression. Here we're going to compute the sine of tan inverse of x plus cosine inverse of x. Just like before, I'm going to take our two inverse trig functions inside, and I'm going to set them equal to angles. I'll set tangent inverse of x equal to alpha, and cosine inverse of x equals to beta. And then I'll flip those statements inside out and rewrite that as tangent of alpha equals x over 1 and cosine of beta equals x over 1. So you might be thinking that you should have just written tangent alpha equals x and cosine beta equals x. And while you would be correct, we got to remember we are dealing with trig ratios here. It's going to make the triangles easier to fill out when we actually can realize the tangent of alpha and the cosine of beta as fractions. So let's draw all triangles and fill these out. With respect to alpha, the opposite side is going to be x and the adjacent side is going to be 1. And with respect to beta, the adjacent side is x and the hypotenuse is 1. Now, I still need to use the Pythagorean theorem to figure out the missing side lengths that we have in each triangle. And since I've already used the variable x, I'm going to label each missing side by the letter y. I can still use the Pythagorean theorems even though I don't have actual values for x or y. For the first triangle, I'm going to get that y squared equals to 1 squared plus x squared, which means that when I solve for y, I get that the hypotenuse length of the first triangle is the square root of 1 plus x squared. For the second triangle, I'll get that x squared plus y squared equals to 1, where again y is the missing side. And when I solve for y, I'll get that missing side length is going to be the square root of 1 minus x squared. So again, even though I don't have a lot of numbers in this problem like I did in the last one, that's okay because we are aiming for a purely algebraic expression. But now that I'm here, I've got two fully filled in triangles, so I can revisit the original expression of sine of tan inverse of x plus cosine inverse of x, and rewrite that as the sine of alpha plus beta. And then I'm going to replace sine of alpha plus beta with the corresponding sum identity. So I am once again in a situation where I'm taking sines and cosines of alphas and betas. Since I have two fully filled in triangles, I can complete that task in the following way, just with the understanding that I'm going to have a lot of algebraic expressions here. Once I go through all these trig ratios, I get the following expression. And after a little bit of work, this is going to simplify to the final answer of x squared plus the square root of 1 minus x squared, all divided by the square root of 1 plus x squared. So if you see a problem like this, you can pretty much expect a lot of your triangles to look very, very similar to this. When you use the Pythagorean theorem on a triangle that has two sides labeled 1 and x, then you're going to see a lot of quantities like the square root of 1 minus x or the square root of 1 plus x or some other combination of those two characters. Alright, well thank you so much for watching and join us again in section 8.3.